Hello and welcome to Aerodynamics course. Within this course, we're going to discuss many things. It will cover a lot. So, the menu is about fluid properties and flow analysis, INVISCID, incompressible flow, airfoil theory, finite wing theory, boundary layer theory, which is the layer between the flowing liquid or fluid or air. That's the layer. It's like the layer where you have the highest viscosity between the air scraping against a surface and the surface itself. It forms what we call a boundary layer that can be laminar, which means that it's going in a perfect curve along the wing, or turbulent, where you have vorticity, and finally compressible flows, where it's the opposite of incompressible flow, where density does not change and temperature and pressure does not change. Incompressible flows, you have a change of density, you have a change of temperature and pressure. All right, let's start with the type of flows, incompressible versus compressible flow. At first, for incompressible flow, you have the density rho is constant, which is the mass of the air per unit volume. It is constant throughout the flow. This is valid for Mach number. By the way, Mach number m equal 1 is the speed of sound. So for whatever velocity value that is less, not of the speed of sound, but less than 0.3, for m less than 0.3, you have the density constant, you have a constant pressure, constant temperature. The characteristics of such flow, it is easier to analyze mathematically for low speed vehicles such as propeller aircraft, such as given as an example, single engine Cessna and twin propeller engine aircraft. On the other side, or opposite to that, for compressible flows, the density changes significantly due to higher pressure and temperature. This occurs for Mach number m greater than or equal to 0.3, which changes all the dynamics of the study of the flow around the wing for aircrafts. It uses isentropic flow relations. Now, isentropic means that it is on one hand adiabatic. In other words, there's no heat transfer. This is what it means. There's no heat transfer from or to the system. And reversible, in other words, there's no loss of energy due to friction or shock waves. So there's no significant drag. There's no friction or shock wave that can waste the energy. So this is called also an entropy change compressible flow. All right, there's no entropy change. What does we mean? What does it mean, entropy? It means that there is turbulence, there's loss of energy, and there's heat transfer. So there are irregularities within the flow. Non-reversibility is due to friction, viscous effects, which is related to the viscosity of the air or the fluid, whatever it is, and boundary layers, meaning in the layers that are close to the wing surface. Shock waves, which cause energy dissipation and increase entropy. Here we go with entropy again. Heat transfer, meaning that the heat is being transferred through the wing, for example, to the outside or vice versa. So you have a loss of energy, and turbulence also causes a non-reversibility because there's a waste of energy, waste of power. This, of course, refers to, when it comes to turbulence, to non-laminar flow, when the flow is no longer following regular curves around the wings that you see or observe within a wind tunnel. When you see the smoke going around a curve, the curve of the wing, perfectly forming streamlines. This is what we call. So non-laminar flow or turbulent flow when you have vorticity, when you have rotational flows around the wings, and drag. Entropy, S, measures the amount of disorder or irregularity that leads to energy loss in a system, rendering it irreversible. So isentropic means there's no entropy, there's no irregularity in the flow, there's no heat transfer, there's no turbulence, so there's no waste of energy. There's no turbulence or friction or drag or any of that. Types of flows: subsonic, transonic, supersonic, and hypersonic. Let's start with subsonic flow. That is for Mach number m less than 1. In such case, the flow speed is lower than the speed of sound. The air streamlines are smooth and curved around the wing surface. There's low air compression, so no variation of density, temperature, and of course the pressure is constant. Most commercial aircrafts cruise at this level, like the Boeing 747, Boeing 737, 777, etc. Now, for transonic flow, where the Mach number is around 1, that would be the image over here, you get both subsonic and supersonic regions exist. So there are regions where you have a high pressure and regions where you have low pressure. So you get this profile over here against this profile where you have only a subsonic flow. Drag increases significantly. There's a drag divergence because of shock waves that can form on the surface. This is when you get, the shock waves forming, but there's no sonic boom yet. There's no crossing or trespassing the speed of sound. However, these shock waves start to induce drag against the airfoil. Supersonic flow. This is when we cross over the speed of sound. That's for M, which by the way, the Mach number is greater than 1, 1 being the speed of sound, and less than 5, you have strong air compressibility. The air is compressed, so there is a change of the characteristics of the air, meaning the density. There's what we call intermixing. There's a higher temperature for the air, which is, by the way, changes the pressure. Shock waves dominate the flow. A remarkable change in air density and temperature, what we spoke about, due to the high pressure of the fuselage against the airflow. So in other words, to put them in order, when you get M greater than 1 and less than 5 actually, but within this range, you have the air is being compressed, you get shock waves dominating the flow, and a remarkable change due to the pressure, because you are compressing the air as you go into that range of speed beyond the speed of sound. So the density changes, the air pressure, because of the air pressure change, and there's a high temperature due to the high pressure, okay, of the fuselage against the airflow, because it is dragging, there's a friction against the airflow, so it changes the characteristics of the airflow around the wing. For hypersonic flow, and by the way, this increases drag, hypersonic flow, Mach number M greater than 5, that's 5 times greater than the speed of sound. You get extremely high temperatures due to air friction against the wing and the body of the aircraft, air dissociation, so you have the atoms of the air are being dismantled, they are being broken down. You have a change of the characteristics of the air, even more so than the previous case, releasing charged particles. So you have ionization of the air, which forms the plasma, by the way. This is what you see during re-entry of the spacecraft in the atmosphere. This is why you see that overheat, because of that plasma layer. This is caused, or this is due the ionization of the air, meaning that due to the high friction, high temperature, there's a change of the characteristics of the air. There's a release of particles. So you get charged ions, positive and negative. You have release of electrons and atoms of the air that are charged positively, creating that layer of charge of ionized particles. We also call plasma. So this disrupts the electrical equilibrium, okay, and leads to ionization. Hypersonic flow study is needed for aerospace applications such as spacecraft re-entry into the atmosphere. Types of flows, laminar versus turbulent flow. So what is the difference between the two, and what is laminar flow and turbulent flow? Let's start with laminar. Laminar flow is smooth, characterized by layers of fluid. This is what we call a formation of streamlines around the wing. This flow is stable and predictable. It has low skin friction, drag occur for lower Reynolds numbers. We're going to talk about that. Now, the Reynolds number is equal to inertial forces divided by viscous forces. The inertial forces are the forces that are pushing the fluid to flow. They are like engaging the fluid in a way to encourage it to flow. Divided by viscous forces are the forces, viscosity is actually an inertial or an internal force that pulls the molecules of the fluid together, resisting against the flow. Okay, it kind of attracts them together and pulls them also closer to the wing. This usually the viscosity is the highest near the wing skin. In other words, a clear example of or like an easy example for viscosity is when you drop water over, let's say, a glass window. You see or you notice that the water does not completely slide off the window. Some of the water remains attached to the skin, to the external skin, okay? And you feel like the tendency that it's pulling together, resisting against the flow, against that drop of water, sliding from top to down. Meanwhile, if you do the same thing with mercury that has much less viscosity, you see that the drop of mercury will slide without leaving any trace on against the slanted window of glass. All right, so this is what we mean by viscosity. So you have, for lower Reynolds numbers, you have higher viscosity, so more laminar flow, meaning that now, of course, there would be a flow, but the flow won't be turbulent. Okay, so this is what we mean by a lower Reynolds number. Meanwhile, you look, okay, for lower Reynolds numbers, you get a higher viscous forces. Yes, they are high, but they maintain the flow together, not to make it completely turbulent. All right, so it helps the flow form in a streamline, kept and compact together, like following the curvature of the wing. Okay, we're gonna see that more clearer in the next slides, I believe. Now, for turbulent flow, turbulent means that it is very chaotic, swirling. It's completely detached. The molecules of the fluid are completely detached from each other. There are no streamlines like the lines of smoke around the wings that form when you see it in Ames Research Center, for example, during wind tunnel tests. So for turbulent flow, you have a chaotic and swirling motion of air, like in a vortex shape. You have a high vorticity. This flow presents higher energy loss. It's not compact together, it's not kept together, but it's more resistant to flow separation, meaning that separation between the boundary layer and the wing surface occur for higher Reynolds numbers or low viscosity. In other words, when you have turbulence, is that it is when you have a low viscosity. In other words, you have the inertial forces that are pushing the air or the fluid to flow are much higher than the viscous forces. It's like when the air versus water, when the water is sliding against a surface because it has a high viscosity, you see that the water follows the curvature of the wing or the surface. Meanwhile, we can compare the water flowing with the air flowing. The air is not as laminar as the water, so it is more detached from the surface, and it's more turbulent, meaning that there are more vortices, okay, at the same speed between the air and the water itself, because the water has a higher viscosity. I hope it gets more clearer afterward, or it is already clear. So occurs for higher Reynolds numbers or low viscosity. Viscosity is the measure of a fluid's resistance to flow. In other words, the rate of friction between its own atoms. That gives a tendency for a fluid to stick longer to the surface and to itself instead of flowing, of sliding in the flow. In this illustration down below, we see, you notice that for the laminar flow, the vectors, the velocity is more stable, okay, there are no vortices. You have, meanwhile, for the turbulent flow, the velocity vector are so random, they are twirling, so you have a rotational flow. This is what we call it. The U is the variation of velocity during time. So for laminar flow, the flow is stable speed-wise, it doesn't change. Meanwhile, for turbulent flow, the speed vectors are chaotic, they are changing. They are all over the place. And down below, that's a representation of flow against a sphere that's above. You see here for a laminar flow, the flow is steady, there are no turbulence. Yes, of course, there are vortices at the back of the bow. It starts to form vortices. However, for a turbulent flow, you see how irregular they are. There's no steady flow. It's much chaotic, okay? And you have the formation of... All right, so type of flows, viscous versus inviscid. Inviscid means that's the opposite of viscous, by the way. So for a viscous flow, viscosity of the fluid is considered. This is the state of the flow near surfaces, such as winds for planes and propellers for ships, okay? The surfaces being. That's actually wings, not winds, for planes and propellers for ships. So viscosity of the fluid is considered especially for the flow near the surface. This is where you see a viscosity being, taken into consideration near the skin of the wing. That's a wing section. Meanwhile, for inviscid flow, it leads to a more turbulent flow which characterizes regions away from the surface. As you notice, okay, so the flow is more viscous near the surface, but when it goes away, when it's being, far, when it goes further from the surface, it starts to form vortices. It starts to become more turbulent. This is what we mean. Inviscid means that the viscosity has no effect. That's for the areas away from the wing. And that's also for the back of the wing. Once the flow has slid away from the wing, it starts forming vortices. It starts actually transforming from a laminar into a turbulent flow. This is where you get what we call a wake turbulence, a wake vortex. That's what you see at the tip of the airplanes crossing the sky, the commercial airplanes. You see these swirling spirals of air. That's a wake turbulence, okay, due to the variation of the air pressure from the upper camber or the upper of the wing to the lower of the wing. So it shows after the flow is done at the tip of the wing, after the flow crosses over. Type of flows: attached versus separated flow. Attached flow is when the flow remains drawn to the surface. It adheres to the surface in a very near proximity. This type of flow maintains lift and reduces the forces of drag. Meanwhile, the other type, which is a separated flow, the flow detaches from the surface. This is when what we call the boundary layer, which we will explain later, detaches from the skin. It becomes much divergent from the skin of the wing due to a high aerodynamic pressure and an adverse pressure gradient or gradients. This separation of flow increases turbulence and causes a degradation of lift, also known as stall, and an increased drag. Now let's talk about Reynolds number, RE. Reynolds number is a measurement factor used in fluid. It has no unit to it. Used in fluid mechanics to assess whether the fluid will exhibit laminar or turbulent flow. RE is equal to rho VL over mu. So let's break it down. Rho is the density of fluid, which is in kilograms per meter cube, mass for unit of volume. V, velocity of the fluid, of the flow in meter per second. L is the length of the section of the wing, if you will. Mu is the dynamic viscosity, also known as viscosity, measured in Pascal per second. And of course, rho over mu is what we call nu, or kinematic viscosity, expressed in meter square per second. Reynolds number, in other words, is equal to inertial forces that push the air or the fluid to flow, divided by viscous forces, or mu. Inertial forces push the liquid toward the flow stream, increasing the flow tendency. Viscous forces, however, are attraction forces. That's also the internal friction of the fluid that pulls the fluid together and resists the flow. It pulls it together and against the surface. Reynolds number is a measurement factor used in fluid dynamics to assess again whether the fluid will exhibit laminar or turbulent flow. So let's talk about different values for Reynolds number. For RE less than 2000, the flow type is laminar and smooth. In other words, that it is of course. Now you would think, but okay, if RE is less, then mu is a bigger value, correct? Why is the flow is laminar and smooth? It's supposed to resist the flow, correct, but it actually does not completely stop the flow. It makes it more laminar, meaning that it follows a specific curvature around, actually it follows the curvature of the wing surface or whatever surface is flowing above. Low Reynolds numbers means higher viscosity. So an example of fluid that has this behavior is the syrup. It flows around the surface. It doesn't detach. The boundary layer becomes, close to the surface of the flow. For a Reynolds number between 2000 and 4000, the flow type is transitional, and it switches between laminar and turbulent. So switching from laminar to turbulent among its characteristics. So it's unstable and unpredictable in such case. For a Reynolds number greater than 4000, the flow becomes more turbulent. That's when we start seeing the detachment of the boundary layer from the surface, or the layer of the fluid that is around the surface curvature. It becomes, or it exhibits, a more turbulent and chaotic flow. In such case, the viscosity is very weak, which increases the Reynolds number. So the flow becomes more chaotic, more turbulent. It's no longer keeping in line. It's no longer curved. It's no longer layered. It is governed by a higher inertia, which is rho VL, that detaches the streamlines from the surface area and increases the vorticity or the rotational flow. Example for that, a very fast air flowing around a rocket or an object. Viscosity. Now for the viscosity, you have the viscosity of the air is 1.8 times 10 to the power of minus 5 Pascal per second. Very weak viscosity. That's why it flows much better than water and other fluids. Extreme fast flow. For water, 1 times 10 to the power minus 3 Pascal per second. So it's much higher than air proportionally. And you notice that the water flows much slower than air, and it sticks much better to a flowing surface. That's why, it creates a more laminar flow rather than a turbulent flow. You experience that in a rivers, where you see that the flow of water around surfaces, around rocks, is much laminar than turbulent. There's no such high turbulence around surfaces of flow for water. Why? Because it's much more viscous. For honey, the viscosity is very strong. That's 10 Pascal per second. This is, by the way, what explains why the honey flows very slowly. It sticks together much, the internal friction, the internal nuclear, or not nuclear forces, the internal attraction forces are much stronger. So it's kept together. It flows very slowly, and it's held together during the flow when it's flowing around the spoon. That's why it takes so much time to drop from the spoon to the bread on your table. So it's very strong, very viscous, and flows very slowly. Motor oil, not as viscous as the honey, but it is very strong, high viscosity, very thick, and it has a very slow flow. Fluid density. Now the density is the mass of the fluid per unit volume expressed in kilograms per meters cube, which is denoted by rho. Rho equal m over v. M being the mass in kilograms, v is the volume in meter cube. Higher density fluids provide higher inertia and affects Reynolds number. It increases Reynolds number. That's why, higher density. For higher density fluids, you have a much turbulent flow, given that density is proportional to the Reynolds number. This factor appears in dynamic pressure, which is the pressure of the moving fluid going through a virtual window or opening area, not the one applied against a surface. If you will, that's the moving pressure of the air around the wing. So expressed by Q in Newton per meter square is equal 1/2 rho v square, and there's no A actually here. You add the A, yeah, that's a note here. You add the A when we're talking about the lift, not the dynamic pressure. Dynamic pressure alone is 1/2 rho v square. When you multiply by A, and you have also what we call the lift coefficient, CL, that becomes no longer the Q formula, but rather the formula for the lift of the wing. Okay, so again, for higher density you have a higher dynamic pressure, and this also increases the Reynolds number, so it increases the flow. Fluid temperature in compressible flows such as gas out of a jet engine, density varies with high pressure and temperature. So due to higher pressure, you have an increase of density and intermixing of air molecules, and the temperature spikes, it increases. However, for incompressible flows, temperature influence is often negligible because there's no change of temperature. However, in both cases, you have the formula for the pressure is equal to rho RT, rho being the density in kilograms per meter cube, times R, which is the gas constant. It's different for each type of gas, and multiplied by T, which is the temperature in Kelvin. Let's talk about static pressure again versus dynamic pressure. The static pressure in Pascal or Newton per meter square is the pressure exerted by a fluid against a surface area. P equal the force in Newton divided by the area. So it's the distribution of the force over the area. This is what we call pressure. Area, of course, expressed in meter square. As an example, what is the static pressure exerted by water within a cylinder of 1 meter height and 0.5 meter radius against the bottom of the barrel? Rho of the water density is 1000 kilogram per meter cube, and gravity G is 9.80665 meter per second square. Of course, you can pause the video and try to solve it yourself. Let's at first start with the volume of water. So the water volume is equal to the surface of the section, which is in a cylinder. You have a disk surface, okay? The area of a disk, which is PR square, multiplied by the height of the cylinder. This gives you the volume of water within the cylinder. We're getting the volume because out of the volume we can get the mass of water in order to get the weight of the water in Newton and try to see or to measure the static pressure through that, because the weight of the water expressed in Newton is the force, and for the area, that's the area of the disk we've talked about. The bottom of the barrel is the area of the disk, of a disk. So V equal pi r square h equal 3.14, that's pi, 159265 times the radius is 0.5 square times the height is 1 meters, that's 0.785 meter cube. Okay, now the mass of the water, you know that rho equal m over v, so the mass of the water equal rho times v, which is rho of water 1000 multiplied by the volume, which is 0.78539 meter cube. This gives you 785.398 kilograms. Now, the weight is the force exerted against the bottom by gravity. So, weight, or it should be W, okay, is equal mg, that's the mass multiplied by the gravity force, the gravity pull of the Earth. So, the weight is equal to 7,702.125 Newton. Finally, the pressure against the bottom is P equal F over A, or the weight over A, equals 770.2.125 divided by PR square. That's the same value here because the volume was multiplied, the surface was multiplied by 1. That gives you 9,806.65 Newton per meter, or Pascal. Dynamic pressure of a fluid is the pressure in motion associated with its kinetic energy per unit volume. So that's the pressure of the fluid in motion associated with the kinetic energy per unit volume. The kinetic energy, actually, that's 1 over 2 mv squared for solid bodies. But for a fluid, it's 1 over 2 rho v squared, rho being the density, v is the velocity of the fluid, the velocity of the free stream flow. So what is the dynamic pressure as an example? Q of gasoline flowing through a pipe traveling 3 meters per second, where the density of gasoline is 775 kilograms per meter cubes meter cubed. By the way, we note here that this density changes for gasoline for different temperatures. So for a higher temperature, you have a lesser density because the molecules are detached from each other. It becomes lighter. So Q equal 1/2 rho V square equal 1/2 775 kilograms per meter cubed times 3 meter per second square, which gives us 3487.5 Pascal. Now, if you imagine that dynamic pressure hitting a surface, it translates into a static pressure. Streamlines, path lines, and streak lines. At first, what is a streamline? That's the line tangent to the velocity vector of the flow at every point. So you have a flow like this curvature over here. These are the vectors that are tangent, or these are the lines that are tangent to the velocity vectors. These, imagine velocity vectors over here with the streamline tangent to these vectors that are going in this direction from left to right. It represents the direction of the fluid, or the fluid will travel at a given instant. In steady flow, streamlines are fixed in their spatial position. They don't move, they don't change with time. But in unsteady flow, like the turbulent flow, they have a probabilistic distribution, a probabilistic changing position. Streamlines are used to visualize fluid flow lines over wings or airfoils to identify laminar versus turbulent flow. Laminar flows, by the way, are identified through constant curvatures, these like perfect curves around an airfoil. Meanwhile, a turbulent flow, you would see it, through vortices within the flow, irregular movement of the air particles. This is what designates a turbulent flow. The path lines. Now, the path line is the actual path for a single particle as it moves through the flow. It's not necessarily exactly the same direction as the streamline. That's the actual trajectory distinct from the overall streamline. For streak lines, it portrays the full trajectory behavior of all particles that passes through a common point in space. They are visualized using the smoke in labs like Ames Research Center. In steady flow, streamlines, path lines, and streak lines overlap together. They are the same. Let's talk about Bernoulli's law, which is for INVISCID or non-viscous flows. For, of course, INVISCID incompressible flow types. Incompressible again means that there's no air compression, the density and pressure does not change, or the temperature does not change. And INVISCID means that the viscosity does not have, or it has a negligible effect when it comes to the flow itself. According to Bernoulli, the pressure of a fluid is a constant. In practice, let's say a fluid is flowing through a pipe with wide and narrow boundaries. The same amount will be flowing across the entire pipe for the wide regions and the narrow regions of the pipe. Now, in wider boundaries, in wider crossings, a large quantity flows slower. So you have a higher static pressure, but a lower dynamic pressure. Why? Because the dynamic pressure is related to the velocity of the flow. But in narrow boundaries, the same amount will flow quicker, increasing the dynamic pressure, but with lower static pressure. Why? Because it's not stagnant. In narrow boundaries, the same amount is flowing quicker, meaning that the dynamic pressure is high, okay? And on the other hand, the static pressure is low. Why? Because it's moving fast across that section of the pipe where it is narrow. So the formula here is P plus Q plus rho GH, which is, the potential energy of the fluid, is equal to a constant. Now, rho GH is not taken into consideration. Why? Because the height, h, which is the height or the elevation of the pipe, is very negligible, which is the elevation between the air particle and the bottom of the pipe. Meanwhile, what counts the most is the static and dynamic pressure. And these two, so rho GH is negligible, static and dynamic pressure are a constant. Now, Again, rho gh is the potential energy with h representing the elevation. So this factor is not considered in most cases because the elevation is almost the same throughout the flow path, being subject to very tiny changes that we don't account for. What counts is static and dynamic pressure, which is a constant. Now, the pressure constant is so significant to determine the behavior of a fluid when flowing through an environment, because we can conclude that static and dynamic pressure work against each other and or inversely proportional. So what do we mean by that? They are inversely proportional. When the velocity v increases, q or dynamic pressure increases. As a result of that, static pressure p decreases so as to make the entire equation constant. It decreases at that point. An example is the air flowing with high speed over a wing will have its streamline curve detached from the wing, creating a vortex area. So this will form a low static pressure area because it's no longer pushing as hard against the wing. Meanwhile, the dynamic pressure will overcome the static pressure. The dynamic factor or the dynamic part of the pressure will become much stronger than the static one. The opposite of that is the air flowing with a low speed v decreases dynamic pressure q, right? Because it's flowing at a low speed. So it means that the streamlines will follow the wing's curvature as air molecules exert a higher static pressure p against wing's surface. A physics explanation at the molecular level: higher speeds increase Reynolds number. Why? Because Reynolds number is equal to rho VL over mu. So it's proportional to the velocity of the flow. This leads to a more turbulent flow while reducing the viscosity. Why? Because they are inversely proportional, which is, by the way, the inner force pulling air molecules together of the fluid. The fluid molecules are pulled away from each other in this case. Okay, they are like more detached from each other because the flow or a high velocity will overcome the resistance, the inner friction of these air molecules. But for lower speeds, Reynolds number, which is proportional to the fluid's velocity, decreases. So the shear stress, which is the pressure vector parallel to the flow, becomes weaker than the inner force pulling the fluid molecules together. So the shear stress or pressure vector parallel to the flow, it becomes more weaker. Then the inner force, the inner friction of the fluid molecules identified by viscosity that pulls these molecules together, attract them together to the flow surface. This leads to a more laminar flow where the streamlines remain close to the flow surface. In aerodynamics, this translates into a flow following the curvature of the wing. This is what we mean by a laminar flow. Let's talk about Newton and Poiseuille's law. Okay, Newton's law. Based on Newton's law, the shear stress tau is related to the dynamic viscosity, or viscosity in other words, of a fluid, and the velocity gradient perpendicular to the flow direction. So higher viscosity is associated with higher shear stress. In other words, more pressure would be needed to separate the molecules of a fluid, contributing to an overall resistance against the flow. This is what we mean. So the shear stress, put it simply, is the required amount of pressure against internal attraction forces of the fluid against the viscosity, keeping the molecules of a fluid close together to enable them to flow, to push them to flow. The U gradient is the normal velocity vector against the fluid. All right. So the U gradient is the velocity vector that is pushing against the fluid. Normal velocity, okay, but it is parallel to the direction of the flow. Poiseuille's law describes the laminar flow through a cylindrical pipe, and it quantifies how the flow rate depends on the fluid's properties and pipe geometry. So Q, which is the volumetric flow, of course expressed in meter cube per second, how much volume is crossing the pipe per second, is equal to pi 4 r to the power of 4, which is the pipe radius, delta P, or pressure difference between the ends of the pipe, divided by 8 mu L, mu being of course the dynamic viscosity, which works against the flow. That's why it is inversely proportional to the volumetric flow rate, times L, because the length of the pipe increases the pressure the static pressure increases the friction or the drag, which also works against the volumetric flow. So it makes so much sense. Let's talk a little bit about potential flow theory, which applies for INVISCID or non-viscous, non-compressible fluids. So this applies again to INVISCID incompressible flows, assuming a neglected viscosity effect on the flow. So there's no internal friction between the fluid molecules and the density rho is constant. In such case, vorticity or rotational flow when molecules travel circular paths is zero, okay? That's the rotational flow. Vorticity means you have vortices, you have spiral trajectories for air molecules or the fluid molecules traveling. It is not in such case incompressible INVISCID flows, so W is equal to the vector of, or the divergence of the velocity vectors, okay, which is equal to 0. In such case, it is not. The velocity potential phi, that's a scalar function defining or defined on all axes pertaining to the motion xy z. On xyz axis, v equal the divergence of the velocity potential throughout the path of the flow. Okay, that's the velocity that expresses how the changes or how the velocity vectors change throughout the flow path. KUTTA-JOUKOWSKI or Joukowsky theorem. KUTTA-JOUKOWSKI theorem is fundamental in aerodynamics to relate the lift generated by a rotating object such as an airfoil moving through a fluid to the circulation flow around it. Now, what is circulation? Circulation is the sum or integration of all velocity vectors of a velocity field around a closed curve or closed loop of an airfoil. This assumes, of course, an INVISCID, non-viscous, and an incompressible and steady flow condition. It is derived from potential flow theory. This law is. It applies to the trailing edge of an airfoil to ensure a finite value of circulation. So the formula of circulation, which is gamma, is equal to the integral around a closed loop or a closed curve, which is the C curve, of, that's the sum of all velocity vectors throughout this curve. L prime, which is the lift per unit span, Newton per meter, that's the expression, it's expressed in Newton per meter, is equal to rho V times gamma, with rho is the fluid density, kilogram per meter cube, times the velocity of the fluid, and times the circulation sum. In other words, the lift is proportional to the density, so for higher density and for higher speeds, for much steady and higher circulation values, you have a more powerful lift of the wing or the airfoil, or lift of, it could be an object moving through water, so it's the same principle that applies. Airfoil theory and lift. At first, let's look at a section area of the wing. So this is what the wing would look like if you're looking at the airplane sideways. So you're observing wing, the transversal section of the wing. This is how it looks like. It's curved on the upper camber. The upper camber, by the way, is the upper area of the wing, and the lower camber is the lower area. All right, so the upper camber, if you look at it, it's more curved than the lower camber. So let's break it down. At first, you have the leading edge. The leading edge is the part of the wing, the front part of the wing that hits the flow. This is the one crossing the flow and cutting through the airflow. We call it the leading edge. That's the front edge of the wing. Opposite to that, you have the trailing edge, which is the rear end of the wing, the rear side, the one from behind. This is the trailing edge. This is where the flow quits the wing. So the flow starts from the leading edge all the way to the trailing edge. The upper part of the wing is called the upper camber. The lower part is the lower camber. And how they are divided? They are divided by a virtual line called a chord line. That's the chord line. That's a virtual line that connects the tip of the trailing edge all the way to the leading edge of the wing. All right, now this is the angle of attack, so which is the angle formed by the flow direction. Let's say the flow direction is from left to the right, horizontally to the horizontal plane. The chord line is, of course, the line, the virtual line connecting the leading and the trailing edge. The angle formed between them is the angle of the attack, angle of attack of the air flowing against the wing. This is what we mean by that. So that's the airplane path. That's the relative wind. The angle between the relative wind and the chord line is called the angle of attack. So the camber of a wing is the curvature of the top and bottom surfaces. Curvature on the top is more accentuated, meaning it's more curved than the lower camber, where it is more flat. Lower camber is more flat. This allows air molecules to flow more rapidly on the upper camber, increasing the velocity and, of course, as a result for that, increasing the dynamic pressure versus the static pressure that is, higher on the bottom, at the bottom of the wing. In contrast, the opposite happens over the lower camber. The air flows more slowly because there's no curvature, and since it's more flattened, you have a higher static pressure. So it reduces the circulation of the air, okay, but you have more push, more static pressure than dynamic pressure. So that's why the dynamic pressure, or in return, the dynamic pressure slows down on the lower end of the wing, on the lower camber. So in other words, the static pressure at the lower camber of the wing is greater than that at the upper camber. Why? Because the air is moving slowly at the lower camber. This is what creates lift. It starts pushing the wing from the bottom all the way up. This is what creates lift. So again, let's make it more simple, more clearer. On the upper camber of the wing, the wind you see here, it's more detached from the wing. It flows much faster. Why? Because it's following a curvature. Here the line or the trajectory of the wind is much longer than that at the lower camber of the wing. Okay, so the trajectory followed by the wind on the upper camber, it's a longer path than the one following, than the flow that's following the lower camber. According to Bernoulli, the air that's flowing from the leading edge, okay, whether it was flowing from the upper camber or the lower camber, it should arrive at the same moment at the trailing edge. Since on the upper camber it's following a longer path, it needs to travel at a much higher speed. That's why you have the dynamic pressure above is much higher than the dynamic pressure below. And of course, since we have a pressure constant, when the dynamic pressure is high on the top, you have a lower static pressure because the air molecules are traveling fast and they are more detached from the wing, if you will. So you have a lower static pressure on the upper camber versus a higher static pressure on the lower camber where the air is traveling at a lower speed. That's why you have a created lift. To give also a more simplified example, let's say two people are descending from a building. One is using the stairs and the other is using the elevator. The one moving through the stairs, since he is following a longer path, he needs to travel very fast downstairs to reach the bottom and to get to the first floor or the ground floor at the same time with the one who traveled via the elevator. The one traveling via the elevator, he can move much slower. Why? Because he's traveling a lower distance. And again, with lower distance, with smaller distances, you can travel much slower. This is what's happening with the air on the lower camber. It's traveling slower, so you have a higher static pressure. The air on the upper camber, it is traveling faster, so you have a lower static pressure or a higher dynamic pressure. I hope this is much clearer. So what you have is, for the lower camber, again, a higher static pressure, and this static pressure difference, because on the lower camber the air is moving slower, so you have higher static pressure versus a lower static pressure at the upper camber, which makes the pressure difference pushing the wing upward. This is what creates lift. The translation of that in KUTTA-JOUKOWSKI equation, with higher circulation of the air on the upper camber, you have a higher lift. which is L prime is equal rho V and gamma being the circulation in meters square per second. For the chord line, before addressing the effect that the angle of attack has on lift, we need to refer to the chord line, which we've talked about before, but we need to refer to it again. This is the virtual line that connects the leading edge to the trailing edge here in green. So the leading edge is the front part of the wing and the trailing edge is the rear part of the wing. That's the rear tip from a sectional point of view. The attack angle is the one formed between the flow vector, correct, direction of the wind, and the chord line, which is again an imaginary line leading or connecting the leading and the trailing edge, sticking, by the way, the effect that you have from the angle of attack, let's say you are sticking your hand outside of the car window when it's running and you turn it against the air, the attack angle will increase the pressure, okay? This is the one between the direction of the air and the palm of your hand. That's the angle. The angle is, for your hand, the one formed between the palm of your hand and the flow direction of the air. And what happens is, you see the form or the shape of the wing alone cannot increase the pressure in a way to lift up a very heavy airplane. But when you increase the angle of attack, what happens is that you're increasing the static pressure, which helps the airplane to lift off, okay? And by the way, this also increases the dynamic pressure above the wing in reverse, okay? So the increase of the angle of the attack subject the lower camber to a higher static pressure by exposing more of its flat area against the airflow. At the same time, the flow on the upper camber becomes more detached from the upper wing surface, creating even a lesser static pressure, so a higher dynamic pressure, because the curvature of the winds on the upper camber becomes like this, okay? So this increases the lift dramatically. Of course, there's a critical angle. You cannot go over it. Otherwise, you would get a more turbulent flow and actually a flow separation, meaning that the boundary of the air flowing through or above the upper camber, okay, could detach from the wing. So this increases the lift dramatically and allows the airplane to actually take off. All right, now let's talk about boundary layer. The boundary layer is a thin layer of air or fluid in general that remains close to the surface of the wing due to its viscosity. This maintains a streamline, you see, that adheres and follows the wing's curvature when the conditions are met for a laminar flow, when you have a normal speed, not a very high speed, when you have a good viscosity, a low Reynolds number in general, because Reynolds number tells all the story, it is equal to rho VL divided by mu. You have a high density of air or a normal density, a good velocity, and not a very high density, but it's reasonable. For low Reynolds number, meaning that the viscosity, the viscous forces are a little bit acceptable so as to make the flow more laminar. They are greater than the inertial flows or the inertial forces that make the wind overflow, okay? The wind flow much higher in a way that is more turbulent. This is what we're talking about. Okay, so you have for low Reynolds number, low velocity, high viscosity, and low density. This boundary layer becomes thicker and more turbulent at the center of the wing, you see here, as the wind starts to slow down and it starts detaching from the surface, as you see. This, the wind starts slowing down due to friction. The point where the flow transitions from laminar to turbulent is called transition point. That's the point where the flow is no longer laminar, it detaches from the surface of the wing. Okay, the boundary layer detaches from the surface of the wing. As speed increases, the viscosity of the air starts to degenerate, correct? So this gives you a higher Reynolds number. Why? Because Re is equal rho VL over mu. And the inertia of the fluid overcomes, the viscosity, the viscous forces, the friction forces, allowing air molecules to flow more rapidly. So they start breaking away even more from the surface. This causes more turbulent flow. This moves the separation or the transition point from laminar to turbulent flow closer to the leading edge. So for low velocity, for low airspeeds, if you will, you have the laminar flow going all the way to the back of the wing. It detaches at the trailing edge. But for higher velocities, what happens is that the laminar becomes turbulent at points that are closer to the leading edge. Meaning, in other words, the transition point between laminar, which is a curved flow, and turbulent, where you have the vortices and the rotational flow, this point of transition moves closer to the leading edge. This is where you have a break of the boundary layer, meaning a separation of the boundary of the layer of air flowing near the surface from that surface. It starts separating. As speed increases, the viscosity of the air starts to degenerate, as we mentioned. The inertia of the fluid overcomes, allowing air molecules to flow more rapidly, and they start breaking away from each other, causing a more turbulent flow. So this moves the transition point closer to the leading edge, as we mentioned. As the angle of attack increases, the flow becomes more disrupted and turbulent. So this leads to vortices forming on top of the upper camber, which increases drag. This turns the laminar flow into a turbulent flow, where air particles break formation and can no longer form cohesive streamlines. Very high speeds provoke almost similar consequences, as the viscosity is depleted and the flow becomes more turbulent. Lift and drag. So lift force is equal to lift coefficient times the dynamic pressure Q times the wing area or wing surface. These two terms, area and surface, are interchangeable. Also equal to, or to break it down, it is equal to CL, lift coefficient, times Q, which is 1/2 rho V square, or dynamic pressure, multiplied by the wing surface area, or S. L being the lift force in Newton, rho is the air density in kilograms per meter cubed, V is the air velocity on the stream or relative to airfoil in meter per second. S wing area can be expressed as S or A in meter square. CL is the lift coefficient, which depends on the airfoil shape, angle of attack, and conditions of flow. Drag force D equals CD QS. So it's almost the same formula, except instead of the lift coefficient, you have the drag coefficient. Drag coefficient, or CD, not CL here, depends on the airfoil shape, surface roughness, and Reynolds number. Let's do an exercise right now. So let's suppose a metallic sphere of radius 1 centimeters is drowning in water of density 1000 kilograms per meter cube of 20 degrees, which means that the dynamic viscosity, or mu, is 0.01 poise or Pascal per second, with a speed of 10 meters per second. What is the drag being exerted against it? Let's at first, in order to find the drag coefficient, we need to find Reynolds number. So Reynolds number for this sphere is equal to rho VL over mu, L being the diameter here, which is the cross distance by the flow of water. That's the diameter of the sphere. V is the velocity in 10, which is 10 meters per second. Rho is 1000 kilograms per meter cube, and mu is 0.01. The diameter is 2 times the radius, which is 1 centimeters, or 0.01 centimeters. Okay, so 0.02 times 10 times 1000 divided by 0.01, so it is 20,000. 20,000, yeah, exactly. We have 20,000, that's the Reynolds number. RE is around 10 to the power of 4. So based on drag coefficient values for a sphere, the drag coefficient in such case, and you look up a table that is related to drag coefficient versus Reynolds number, CD, or drag coefficient, is 0.47. So you have the drag coefficient 0.47, we have all other values, hence the drag against the metallic sphere as it cuts through the water is, note that S is the surface of the sphere exposed to the drag, which is half of the sphere area, or 4 pi r squared divided by 2. That's the surface, the contact surface with the flow, okay? Because 4 pi r squared is the surface area of a sphere from the outside divided by 2, given that we have half of the sphere being exposed to the flow. So, which gives us 0.06283 meters square. So the drag is equal to drag coefficient times Q, the dynamic pressure, times S, equals 0.47 times 1/2 rho 1000 times V square, which is 10 meters per second square, times the surface 0.06283, equal to 1476.505 Newton. Now let's talk about forces acting over an airfoil. You have at first the lift force, which of course that the lift is created by the differential of pressure from the lower camber to the upper camber. You have the drag that pushes against the direction of thrust. Thrust is the force created by the propellers that moves the plane forward, and of course the weight of the wing in such case, or the weight of the airplane. According to Newton's third law, when the vertical sum of all forces is 0, it means that T equal D and the weight is equal to the lift. In such case, you either have a static equilibrium, which is when the plane is on the ground, or a dynamic equilibrium, it is when the plane is moving at a constant speed in the air. Now let's talk about finite wing theory and the first two main phenomena, downwash and induced drag, which are related to each other. Downwash, according to Newton's third law, for every action there's an opposite and equal reaction. Of course, you already know that. So when the airplane's wing generates lift, it pushes the air downward, and as it cuts through the atmosphere with a high velocity. In its turn, the air flows down. The air flowing down pushes back against the wing, which is creating lift here in such case. Okay, so the air that's flowing down, it pushes back against the wing to create lift, the L vector. This downward flow of deflected air is called downwash. This is the downwash. This phenomena is usually more noticeable behind the wing tips, which create the wake vortices, what we call the wake turbulence, these spirals that you see at the wing tips of a commercial aircraft. The swirling spirals you see behind the wing tips of large airplanes, this is what we call the wake turbulence. Induced drag. The other byproduct of lift is what we call the induced drag. So in the process of generating lift, the upward aerodynamic force, not to be perfectly vertical, but okay, it tilts backwards. You see, this means that we have an induced drag being formed. So the upward dynamic force and this pushback of the wind, this also creates an induced drag. Why? Because this pushback is also slowing down the airplane. Okay, and the lift, actually, yeah, the resultant vector from the lift and the drag is not vertical, it's slanted backwards. Why? Because you have a byproduct of the lift is the induced drag during the lift. Why? Because this air that has been downwashed is pushing backwards on the wing. This is the induced drag. So that's why the resulting vector is tilted backwards. This means that this vector, the red one, is the sum of two forces, of which the vertical lift component, which is the blue one, and the other component, which is the induced drag. This type of drag is actually created due to the lift. It is a byproduct of the lift vector. Okay, and this is the one that we call induced drag. We have other types of drag, but this one is generated due to the lift. It is caused by the lift itself, by the lift process. Now, the formula for induced drag. The induced drag is given by di equal pi EQS over L squared. So let's break it down. Pi is the same pi for the circles, 3.14. E is what we call Oswald efficiency factor. It has to do with the lift efficiency of the wing. It's related to the wing form, the wing shape. Q is the dynamic pressure, or 1/2 rho v square, times S, which is the surface area, the wing area, divided by L, which is the lift coefficient. So for higher lifts, okay, more powerful lifts, you have
a lesser induced drag. So the induced drag is counterproductive to the lift. It's inversely proportional to it. Again, Oswald efficiency factor is a number between 0 and 1. That is a measure of how much a wing can generate lift, how much efficient is the wing. So how much a wing can create lift with less induced drag. The perfect ideal wing is theoretical, would have an Oswald efficiency factor of 1. But of course, you always fall between 0 and 1, but for more optimal wings, you get as close as 1 as you can, okay? So, of course, 1 being the idealistic, and by the way, for an idealistic wing, you would get an elliptical shaped wing. This is where you would have an E equal to 1. Now, as a reminder, it is designated as induced due to the fact, the induced drag. It's called induced because it is caused by the lift itself. Lifting line theory, Prandtl theory. A real wing is a finite model that produces a downwash behind, which alters the effective angle of attack, the value of the real angle of attack. This theory is a foundational aerodynamic model developed by Ludwig Prandtl, which is, who is a German engineer in the early 20th century, pertaining to finite aerodynamic wings. The theory relates the geometric attack angle with the downwash induced angle and the resulting lift to come up with a consistent distribution. This theory applies when considering a steady, incompressible and INVISCID flow, a small angle of attack, and a thin wing. Case for most commercial aircrafts. Alright, so the alpha, or the effective angle of attack, is equal to the geometric angle of attack minus gamma y, which is the circulation distribution at a point throughout the curvature, the upper camber curvature, that's y, divided by 4 pi v. V, of course, is the velocity of the free stream of the flow, integrated or times integral between minus b over 2 plus b over 2. By the way, minus b over 2 plus b over 2, both of them form b, which is the wingspan, or the distance from the first tip of the wing to the second wing's tip between an airplane. So you have the airplane over here, you have 2 wings. That's the distance from the first tip to the second tip. This is what we call the wingspan. So from b over 2, from half the distance of the wing span to the other half, integrating 1 over y minus y prime. Okay, these are y being, of course, a point here on the curvature, minus y prime, the other point, actually the point at the center, dy prime. This is what gives you the effective angle versus the geometric angle of attack. Okay, and it relates, it is proportional to the circulation, actually anti-proportional to the circulation. So when the circulation is high, this effective angle would be different from the geometric angle. So the perfect condition is that you have a circulation which is 0, of course, when this entire factor is annihilated. So according to Prandtl's, elliptic wing are the most ideal for well-distributed circulation generating lift with minimum induced drag caused by the downwash. So the circulation at a point y is equal the central circulation, which is the highest circulation, supposedly at the center of the camber, square root 1 minus 2y divided by b squared. Okay, y is a point here on the camber, b is the wingspan or distance from, not distance from trailing to leading edge, distance between the 2 tips of the 2 wings, okay, from the first tip of the first wing to the other side. These are the boundaries, like it's the width, if you will, of the airplane. This is what b is. By looking at this equation, we notice how when b goes to plus infinity, this entire factor becomes 1. So the circulation becomes the maximum circulation. Of course, this is theoretical because the wingspan is always a finite value, but as long as the wingspan is, the circulation would be better. This is what we mean by that. So gamma y is equal to gamma 0 when 2y divided by b becomes 0. That's when b, or the wingspan, is infinity, which provides the perfect circulation, of course. But with smaller wingspans, or when the distance is smaller between the two wingtips, or in other words, when you have shorter wings, you have a lower circulation, not the optimal one. So the maximum circulation along the wingspan, which is typically the circulation value at the center of the wing, is gamma 0. It becomes gamma y. It becomes the same circulation throughout all the wing when you have a very long wingspan. In practice, you won't have an infinite wingspan b, of course, but the geometry that provides the longest span with an optimum flow and less induced drag is the elliptical wing section. Aspect ratio, or AR. What is the aspect ratio? This defines the geometry of the wing. In rectangular simple wings, it's the ratio between the wingspan b and the distance between the tips of the two wings and the chord line. That's the ratio. A virtual direct line, of course, chord line being the virtual direct line connecting both front and leading edge and trailing edge, front and back of the wing. But for general curved wings, including tapered and swept wings, it is the ratio between the square of the wingspan and divided by the wing area. In simple terms, rectangular wings, the aspect ratio for a rectangular wing is b divided by c, b being the wingspan, distance between the two tips of the two wings, okay? We'll see it in the other picture, divided by the length of the chord line, because that chord line has a fixed value for rectangular wings. Rectangular being the shape. If you look from above the airplane, you see a rectangular wing, having the same distance between the trailing and leading edge. But for general wings, especially the swept wings, aspect ratio is equal to b squared, which is the distance from tip to tip, or the width of the airplane, distance from the first wing tip to the second wing tip, squared divided by the wing surface, or the wing area. That would be the aspect ratio. Let's talk about the aspect ratio impact. Aspect ratio is an essential factor that determines the aerodynamic performance of the wing. So we represent the difference between high and low AR in relation to different aerodynamic phenomena or parameters, such as lift and drag. For high AR, higher aspect ratio. Higher aspect ratio means you have a longer wings and narrower wings, where B is very long and S, which is the surface area, is small. In such case, so having longer wings will provide a more lift efficiency, okay? A lower induced drag, because B, the span, as we remember the other slide, the span is very long, but they are structurally weaker because they are more prone to bending and deformation. Tips are very far from the fuselage, and not only that, but the area of contact with the fuselage, with the plane body, is smaller. So it is less compact and less structurally strong or solid. Meanwhile, for low AR aircrafts, low aspect ratio, this means that the wings are shorter, they have larger area in respect of the wingspan, or smaller, and the area is larger. So B squared over S is a small value which lowers the AR. Okay, the distance between tips is smaller, but the area is larger. So you have wider wings but short at the same time. This provides better maneuverability, meaning that the controls have a swift effect when you tip the wing or when you turn. During the turn, the response of the airplane is much faster. It turns very quickly, like the F-16, for example, like the war aircrafts, okay, the fighter jets. So it is structurally stronger. Why? Because the tips are closer to the fuselage, reducing bending, and you have a larger area, reducing bending and deformation. They are less prone to be broken. Plus, you have a larger area of contact with the fuselage, which makes it structurally stronger, but at the same time you get a higher induced drag, because as we've seen, the drag has a direct relationship with the wing area, correct? Larger wing areas induce more drag. Aspect ratio, or AR. By resolving Prandtl's equation, a relationship was established between the induced drag coefficient and the aspect ratio. So with higher aspect ratio, we have less induced drag. Let's break it down for a visualized plane afterward. But at first, let's examine the equation over here. So you notice that the drag coefficient, the induced drag coefficient rather, is anti-proportional or inversely proportional to the aspect ratio. So for higher aspect ratio, you have less drag coefficient, and why? Which means for a higher aspect ratio means longer wing tips and narrower wing surface areas. So for high aspect ratio, you have less drag because you have less drag coefficient value, okay? Also, in the other equation, you see that the induced drag value was proportional to the wing area. Why? Because they correlate with each other. For larger wing areas, you have a much higher downwash, okay, a higher induced drag, and this is why the relationship is that for larger wings and smaller tips, which is a smaller wingspan, you have a higher induced drag and vice versa. So by comparing the equations, you can figure it all out and you can deduce how they are related to each other. Of course, E, the Oswald factor, is related to the lift efficiency of the wing. Below we have the Gulfstream as an example. The wings are elongated and narrow, which means it has a high aspect ratio. Why? Because B is greater than S. As a reminder, for curved shaped wings, the aspect ratio is B squared over S versus B over C, which is C being the chord line for rectangular wing aircrafts, the ones that were used in the First World War, for example. A small surface area S relative to the span means a lesser induced drag during lift due to a smaller downwash, but the fact that they have less wing area can lead to high loading on the wings. So the wings bend, they can actually break over much higher speeds. That's why you have an alarm going off of overspeed when these planes travel at above the speeds designated for them, okay? Because the wings can be distorted, they can even break, they can detach from the fuselage. As for the maneuverability or response to mechanical control of the ailerons are these flaps, not flaps, these layers at the trailing edge of the wings that allow the plane to turn to make a bank roll. This maneuverability for this type of aircraft is slow. In other words, the plane takes a longer time to respond to a bank roll, unlike fighter jets, which can turn drastically and swiftly. The longer the span means the wings are more prone to overbending and structural damage under certain load effects or load given the tips are further from the fuselage, okay? They are not exactly compact as fighter jets, as the wings for fighter jets. Low aspect ratio characteristics. So for shorter wingspan B versus a larger area S, like the wings of an F-16 jet fighter, this means much higher induced drag during lift because you have a lower lift efficiency. So going back to this formula, you see the drag coefficient is inversely proportional or anti-proportional to the aspect ratio. So for higher aspect ratio, you have a lower induced drag, but for low aspect ratio, like for this plane, this sketch down below, you have a higher drag. More structural, on the other hand, more structural integrity, wings are stronger against shear forces, they endure larger loads. That's why the F-16 can turn this drastically without braking during drastic rolls and turns, given their shorter span and larger wing area, which gives us a larger area of contact with the fuselage. High maneuverability, meaning that a lesser adjustment of wing control, such as the ailerons, can make the airplane direction swiftly compared to longer span aircrafts for commercial planes. More tolerant to higher speeds because it's more compact and sudden turns, and can survive heavier aerodynamic loads. That's why it can turn and it can maneuver during war the way it does. Now let's talk about laminar versus turbulent flow boundary layer. Alright, we've already addressed laminar versus turbulent flows, but we did not address what the boundary layer actually is. The boundary layer is a thin region of fluid close to a flowing surface, i.e. wing, where viscosity has a significant effect on the flow. In this layer, depending on the scenario and the flow conditions, airspeed or the speed of the air around the wings, density of the air, attack angle, etc., the flow is either laminar or turbulent. Let's take at first a laminar boundary layer. This boundary layer exists for low speeds and smooth surfaces. The flow in such case is smooth with ordered layers of fluid flowing on top of each other with a regular curvature following that of the wing surface or the flowing surface. Velocity vectors are smooth and parabolic, increasing gradually from the surface. Drag is lower, the flow is less stable and is largely affected by disturbances, meaning that when you have a sudden shift of air pressure, the flow is broken, okay? Or it can be even affected by the rough surfaces such as a formation of ice on the surface and changes in the air pressure. As for the thickness, it usually represents a thinner layer than the turbulent boundary layer. And it's closer, in other words, this layer is closer to the surface of the wing. For turbulent boundary layers, these occur during high speeds and when you have a rough surface like during ice formation on the wings. The characteristics of such a turbulent boundary layer, it is chaotic with higher vortices. You have rotational flows and swirling flows with intermixing in the flow, higher drag and skin friction due to irregular broken air curves, and it's more stable means that it's more resistant to air disturbances, okay? It's not broken easily by a change of density and pressure. Also, on the other hand, this layer is thicker than laminar boundary layers. Laminar profile characteristics, velocity. So the velocity u, which is the velocity of the airflow at distance y from the surface within the boundary, divided by u, which is the velocity of the free stream air, is approximately equal to y, which is the distance from the wing skin, distance from the surface again, divided by delta the boundary layer thickness to the power of n, where n is a number between 1.75 to 2, which represents, it's different for different shapes of wings. So it's related to shape factor or velocity profile, characterizing distribution within the boundary layer. As for the boundary layer thickness, delta Lx is around 5.0 for laminar profile times x, which is the flat plate length, okay, or if you will, the of the chord line, divided by square root of the Reynolds number at x, okay? So now, meanwhile, for turbulent profile characteristics, the velocity is u divided by big U. Again, u or uy is the velocity at distance y from the surface of the wing, which is the distance above the wing from the point of measurement to all the way to the wing surface, divided by capital U, which is the free stream velocity of the air flowing, is approximately equal to y. Again, that's the value of the distance from the surface to that point of measurement divided by the boundary layer for turbulent profile to the power of 1/7. As for the boundary layer thickness, delta Lx is around 0.37 times x, which is the flat plate length, divided by the square root of Reynolds number to the power of 1/5, where the Reynolds number is equal to ux, u is the free stream velocity times the flat plate length, divided by nu, which is the kinematic viscosity, or in other words, it is ux times rho over mu. Mu is the dynamic viscosity. Okay, actually, yeah, 1 over mu, yeah, exactly. So it is rho over mu. You can replace mu by rho on the above, in the numerator, over mu. Now let's talk about flow separation. What is flow separation exactly? Flow separation happens when the boundary layer adhering to a surface detaches from it. This is mainly due to adverse pressure gradients due to the flow overcoming viscosity that keeps air molecules ordered in a streamline curve around a flow surface. Okay, so this usually happens when the fluid slows down to a point where the streamlines become very weak. Okay, the viscosity becomes very weak, and the streamline, that curvature around the wing surface, is easily broken by adverse pressure. The fluid flowing close to the wing surface moves slower due to viscosity. So when the wing crosses a region with a high air pressure, it plucks out, it peels out this fluid, okay, flying or flowing closely to the surface. By the way, such areas would hill areas where you have hot vortices. So if the fluid is moving very slowly, you have low power engine, for instance, low power engine configurations, and hence lower airspeed, the adverse pressure that is pushing against the viscosity, or like the internal friction of the air molecules, can peel out or pluck out the boundary layer away from the wing, detaching it from the wing and leading to flow separation. This is what flow separation means. Now bear in mind that flow separation is detrimental for lift. The consequences would be loss of the lift force at the wing, which technically leads to a stall. This is called a stall, meaning that the wings can no longer generate lift at this point. Large wakes, as you see, rotational swirling of the air above the camber here in this illustration. A wake refers to a turbulent rotational flow around the wings. Increased drag due to turbulence, so the drag increases, and you have low or loss of air pressure in the engines, which means also at the level of the engines, the air would no longer flow normally. So the air may lose or even reverse its flow direction within the engine, starving the engines from air, which is crucial for fuel combustion. This is one of the cases when you get an engine backfire, by the way. So these two types of drag, skin friction drag versus pressure drag, let's talk about them right now. Let's at first start with the skin friction drag. Both, by the way, are parasitic, so they hinder or they stifle the lift or the flow of the air around the airplane. Okay, they stifle the movement of the airplane, and they do not produce the lift. Okay, they do not produce lift, unlike the induced drag. So for skin friction drag, it arises due to shear forces between the fluid and the surface of the wing as the aircraft moves through the air. It affects the boundary layer that is close to the wing surface. So it hits the boundary layer where you have a higher viscosity of the fluid. It is the most active when the boundary layer is close to the surface and its shape is streamlined around the flow lines. The factors affecting this parameter are surface area, surface roughness, viscosity of the fluid, and the flow speed. So these are the different factors that can lead to a skin friction drag. Mitigation strategies for that type of drag would be smoothing the wing surface, controlling the laminar flow, and reducing the wetted surface area. So you have the smoothing of the wing upper skin, controlling the laminar flow, and reducing the wetted surface area. The other type of drag is pressure drag. This type of drag is caused by the flow separation resulting in pressure difference between the front and the rear of the wing when you have a peeling off of the boundary layer. This is what pressure drag is. It is most prominent at the wake regions of the wing where there is no, there is no stable flow, there is more turbulence, and chaotic flows. It is most dominant when there's a separation of the flow. This factor, I mean, actually it can also occur when there's no full separation, like at the center of the wing, it can be occurring. This factor is dependent on the shape of the wing, of course, attack angle, because for higher attack angle you have a higher pressure drag or drag pressure, and also it's dependent on the Reynolds number that has to do with the viscosity, because this dictates whether the flow is laminar or turbulent. Mitigation is by reducing sharp edges around the wing, you know, by placing fillets, delaying the flow separation, and designing more elliptical shaped wings. Mach number and compressible effects. So the Mach number M is the ratio of the current speed V of an aircraft or an object and the speed of sound A. That's the difference between them. So M equal V over A. Of course, when the speed approaches the speed of sound, or rather it is equal than the speed of sound, to the speed of sound you have M equal 1, which is, you know, the speed of the traveling at exactly the speed of sound before the sound barrier break, okay, before the sonic boom. The speed of sound in the air is given by A equals square root gamma times RT, where gamma is the ratio of specific heats, 1.4 for the air, R is the gas constant, and T is the absolute temperature in Kelvin. Compressibility effects. So what are the effects of air compression due to high speeds or due to an object traveling at high speeds shearing through the air, like a meteor? By the way, not only airplanes can do that, even meteors can do that when they cross through the atmosphere. First, you have density changes affecting the overall behavior of the fluid. So the density increases. Why? Because the air molecules are being compressed against each other, so you have a heavier weight per unit volume. Shock waves, and which is, you know, at and above Mach 1, causing sudden pressure, density, and temperature peaks. You have a rise of pressure, of density, and higher temperatures due to shock waves. Increased drag at transonic speeds, meaning that that's the speed when the airplane transitions from a lower than the speed of sound to the higher than speed of sound due to wave drag. Flow choking in ducts and nozzles, meaning that the mass flow rate reaches a maximum, okay? And in other words, you know, there's a choking and a starvation of the engines in such case. Temperature rising due to high speeds, which compresses the air. When the air is compressed, high pressure leads to a higher temperature. This is known for gases. The air remarkably, you know, especially during hypersonic maneuvers, is being compressed. In compressible scenarios, now let's talk about isentropic flow relations. So in compressible scenarios, an isentropic flow refers to an ideal flow, meaning that it is adiabatic, there's no heat transfer from or to the system, to the airplane, and reversible, in other words, there is no loss of energy. So there's no friction or shock. In other words, constant entropy. There's a constant entropy where heat and energy remain stable in the system. Entropy, again, as a reminder, it is due to a turbulent flow, an irregular flow, and a change of density, a change of, actually not change of density, but it's a change of temperature and a transfer of that temperature to the outside of the system. It is the change in the energy transfer, because, you know, there's a loss of energy between the engine, okay, or thrust, and the flow, okay. There's an energy being where heat and energy remain stable. You have a stable and constant entropy. As a reminder, what increases entropy are factors like viscosity, friction, heat transfer, shock waves, turbulence, and molecules of air intermixing. Temperature ratio. Now let's see the relationship of temperature, pressure, and density between T and T0, P and P0, rho and rho 0. Now, P0, T0, rho 0 are the stagnation like respectively stagnation pressure, temperature, and density. Okay, so when the air is stagnant, that's the pressure of the air. That's the temperature of the air when it's stagnant. Okay, it's not moving at a certain point, and its density. So what is the relationship? Again, gamma is the heat ratio, 1.4 for the air, m is the Mach number. So T divided by T0 is equal to 1 plus gamma minus 1 divided by 2. Gamma is the heat ratio times m squared, which is the Mach number, to the power of minus 1. The pressure ratio is current pressure divided by P0, which is the stagnation pressure, equal to 1 plus gamma minus 1 divided by 2 m squared, minus to the power minus gamma divided by gamma minus 1. And finally, density ratio rho over rho 0 is equal to 1 plus gamma minus 1 over 2 times m squared. That's the same factor here, only the power changes, to the power of minus 1 divided by gamma minus 1. Now let's talk about Mach relation in a nozzle. So what is a nozzle? Here we are referring to a jet engine where the nozzle is the point or the area where the air, after being pressurized and after increasing its temperature, it goes thrusting out from the engine with very high speed, creating a momentum that gives a thrust to the airplane or the aircraft. But what is the anatomy of a jet engine? So what is its geometric structure before getting to the nozzle? You have an external fan which has a low compression or low pressure. Its main role is to suck the upstream airflow on the inside to the side of the engine. Then after that you have low pressure compressors. Some of them are turning and others are static. They are alternated. They have the role of sucking as much air as possible, gulping large volumes of air to the inside of the engine. Right after that you have high pressure compressors that turn at much higher speeds to compress the air, to give it, to increase the pressure. And after increasing the pressure of the air, you have the fuel added, and then the combustion, where a large explosion that expands the air. It becomes very hot. Actually, the compression lowers the temperature, and the pressure, compresses the air, lowers the temperature of the air. And after the explosion, it goes out with a very high pressure because of expansion, because the gas expansion and the fuel. And it goes thrusting with a very high speed out of the nozzle. This is what creates the thrust, okay? And of course it turns the turbine to regenerate the electricity, the current for the airplane. Now, for this formula, A over A star, which is the area of the external nozzle, okay? A is the area at any given point within the flow, is equal 1 over m, where m is the Mach number, multiplied by 2 divided by gamma plus 1, gamma is the heat ratio, multiplied by 1 plus gamma minus 1, divided by 2, m squared, all of that except 1 over m on the outside, to the power of gamma plus 1 over 2 times gamma minus 1. This gives us, the Mach relationship to the area of the nozzle and to the area at any given point within the flow. So thank you so much for watching, and see you next time.